Hello dear students, today we are going to start our new chapter from integral transform, that is beta and gamma function. Beta and gamma function. First of all, why we need to find or introduce beta and gamma function. In physics and mathematics, many problems are solved with the help of beta and gamma function. Actually, it associates input and output of output of some transforms, and it helps to solve many problems from physics and mathematics, especially scattering amplitude is solved with the help of beta and gamma function. Beta function is two variable function while gamma is a one variable function. We are going to study the definitions and properties of beta and gamma function, which are useful to solve our basic examples of our lives. So, we are going to start with definition beta function. Beta function. Beta function is denoted by beta function. Beta function is denoted by symbol beta having long tail, and it is defined as beta of mn is equals to integration from 0 to 1 x raised to m minus 1 into 1 minus x raised to n minus 1 dx. Beta function is defined by integration from 0 to 1 x raised to m minus 1 into 1 minus x raised to n minus 1 dx, where m and n are positive, where m is greater than 0 and n is greater than 0. The application of beta function, I have already told you that we can associate input and output of a particular graph with the help of beta and gamma function, and we can solve scattering amplitude with the help of beta and gamma function. It is the main application of beta and gamma function. We have defined that beta is denoted by beta, a b having long tail, and it is defined by beta of mn, where m and n are positive. Integration from 0 to 1 x raised to m minus 1 into 1 minus x raised to n minus 1. Now, properties of beta function. Properties of beta function, that is beta function, there are two important properties of beta function. That are, first of all, it is symmetrical. It is symmetric function. What is meant by symmetric function? Symmetric function means if we take two variables beta m n is always equals to beta n m. Symmetric. Beta mn is always equals to beta nm. This property shows that the beta function is a symmetric function. Now, how to prove beta mn is equals to beta nm? So it is quite easy. Since we know that the definition of beta function, or we can say that the theorem prove that beta function is symmetrical, or prove that beta mn is equals to beta nm. Here we have right or prove that beta function is symmetrical. Means we have to prove that beta mn is equals to beta nm. Or they can simply ask you prove that beta mn is equals to beta nm. Since we know that the definition of beta function, since we know that the definition of beta function, what is that? Beta mn is equals to integration from 0 to 1 x raised to m minus 1 minus x raised to n minus 1 dx. Now we are going to prove beta mn is equals to beta nm, or simply we can say that beta function is symmetrical. We are going to prove beta function is symmetrical. So to prove this theorem, we put 1 minus x is equals to t. Put 1 minus x is equals to t. Then we will get 1 minus t is equals to x, correct? And if we find the derivative, then we get minus dx is equals to dt. One more thing we have found, because we have take 1 minus x is equals to t. 1 minus x is equals to t. Now we have to convert x in the form of variable t. Then we will get from this equation 1 minus t is equals to x. And if we differentiate with respect to t, we will get minus dx is equals to t. Correct? Now x varies from 0 to 1. Since x varies from 0 to 1, what about t? What about t? So we will find the value for t. Since we know that 1 minus x is equals to t, if we take x is equals to 0 in this equation star, then we will get 1 minus 0 is equals to t. This implies that t is equals to 1. Correct? Now, what we have on? We know that x varies from 0 to 1. Correct? We have to find the value of t. We know that 1 minus x is equals to t. If we take x is equals to 0, since x varies from 0 to 1. So we are taking value first 0. 0, x is equals to 0. Then the star becomes 1 minus 0. That is 1 minus 0 equal to t. 1 minus 0 is equals to 1. Then we will get t is equals to 1. Similarly, if we take x is equals to 1, then the star becomes 1 minus 1 is equals to t, and 1 minus 1 is equals to 0. So we will get t is equals to 0. Then we can say that t as x varies from 0 to 1, t varies from 1 to 0. Correct? We have put value of x as equals to 0. We get t is equals to 1. Then we put x is equals to 1. We get t is equals to 0. Then we can say that whenever x varies from 0 to 1, t varies from 1 to 0. Now we convert this integral in the form of variable t. So 0 to 1 x raised to n minus 1, 1 minus x raised to n minus 1 dx is equals to t varies from 1 to 0. X, what we find about x is equals to 1 minus t. So we can write that it as 1 minus t m minus 1, and 1 minus x we have taken 1 minus x is equals to t n minus 1, and dx is equals to minus dt. So we can write it as minus dt. We have converted all the variable of x into t. Now we get integration from 0 to 1, 1 minus t raised to m minus 1, t raised to n minus 1. Now interchanging the limits, we will get minus 0 to 1, 1 minus t raised to m minus 1, t raised to n minus 1 minus dt. And this minus and minus will cancel. We get 0 to 1, 1 minus t raised to m minus 1, t raised to n minus 1 dt. And again we can write it as 0 to 1, t raised to n minus 1, 1 minus t raised to m minus 1 dt. And it is just in the form of variable t. So we can write it as beta n m. So we have proved that beta of mn is equal to beta of n m. Correct? Now many students will be confused in this state. In this state, this one. How we can interchange the integration? Many students will be confused. Maybe confused in these steps. How we can interchange the limits of integration. So it is quite easy to prove. Integration from a to b f of x dx is equals to minus integration from a to a f of x dx. Consider f of x is equals to g dash of x, derivative of gx. So we can write it as ab g dash of x dx. It is LHS. So we will get, after integration and derivative is inverse to each other, or derivative has another name and integration has another name, antiderivative. So integration and derivative get cancelled. We get g of x is equals to limits from a to b. Then we put upper limit g of b minus g of a. We get, we have calculated left hand side. Now right hand side with minus sign, a b to a, f of x we have taken g dash of x dx. Now as we already seen, integration and derivative are inverse to each other. We get g of x, limit from b to a. Now g of a minus g of b, and after taking minus of this, we will get g of b minus g of a, and which is equals to left hand side. So we can interchange our limits of integration. So we have proved beta mn is equals to beta nm, or we can say that beta is symmetrical function. We have proved now. Now take one example, how to calculate value of beta. Before going to start with example, I want to share one more property of beta function in the form of gamma. Beta mn is equals to gamma of m into gamma of n upon gamma m plus n. Since we know that definition of gamma n is equals to 0 to infinity integration e raised to x, x raised to n minus 1 dx. It is single variable function. Now, since we know that gamma of n is equals to n minus 1 factorial if n belongs to integer, positive integer. Correct? So, if you want to find gamma of 3 beta of 3 comma 2, then with the definition or with the property we will get gamma of 3 into gamma of 2 and gamma of 3 plus 2. Correct? Now gamma of 3, since we know that gamma of n is equals to n minus 1 factorial, so gamma of 3 is equals to 3 minus 1 factorial, that is 2 factorial. You will get 2 factorial into gamma of 2 means 2 minus 1 factorial, that is gamma of 5, and you will know that 5 minus 1 factorial, that is 4 factorial. So we can write it as 4 factorial. Now 2 factorial means 2 into 1 into 1, and 4 factorial is 4 into 3 into 2 into 1. So 2 and 2 get cancelled. We will get 1 upon 4 3 is 12. Beta of 3 2 is 1 upon 12. Beta of 3 comma 2 is equals to 1 upon 12, and we can write it as, because beta is symmetrical, so we can write it as beta of 2 comma 3 is equals to 1 upon 12. Similarly, one more example. I am going to take beta of 5 comma 4. So as we know that beta of 5 comma 4 is equals to, or we can write it as, since we know that beta of mn is equals to gamma of m into gamma of n, gamma of m plus n. We are going to find the value of beta of 5 comma 4, and we know that beta of n comma n is equals to gamma of n into gamma of n upon gamma of n plus n. Now with the help of this formula, we will use beta of 5 comma 4 is equals to gamma of 5 into gamma of 4 and gamma of 5 plus 4. Since we know that gamma of n is equals to n minus 1 factorial for integer, so we can write it as gamma of 5 is equals to 4 factorial, while gamma of 4 is equals to 3 factorial, and gamma of 5 plus 4. 5 plus 4 means 9, gamma of 9, and gamma of 9 is equals to 8 factorial. So we can write it as gamma of 5. Gamma of 5 is equals to 4 factorial. We can write as 4 factorial into gamma of 4 means 3 factorial, correct? And gamma of 9 means 8 factorial. So 4 factorial means 4 into 3 into, or we can write it as it is 4 factorial into 3 factorial means 3 into 2 into 1, and we can write 8 as 8 into 7 into 6 into 5 into 4 factorial. 4 factorial for factorial get cancel. 3 to the 6 and 6 get cancel. We will get 1 upon 5 upon 1 upon 280. Right. Beta of 5 comma 4 is equals to 1 upon 280, or we can write it as beta of 4 comma 5. Correct? We have seen the application of beta and gamma function. That is, we can associate input and output of a particular function with the help of beta and gamma function. We have seen the definition of beta function, that beta of mn is equals to integration from 0 to 1 x raised to n minus 1 into 1 minus x raised to n minus 1 dx. We have seen the property about the symmetric property about beta function, that is beta of mn is equals to beta of nm. And we have seen the relation between gamma function beta of mn is equals to gamma of n m into gamma of n upon gamma of m plus n, and with the help of this formula we have solved two examples which are easy to calculate, but we have to know these two formulas, gamma, relation between beta and gamma, and we know that gamma of n is equals to n minus 1 factorial where n is an positive integer. So today we will stop here with completing two examples. Now in the next lecture we will try to solve another property of beta function, and we will introduce gamma function at that time, and we will solve some examples on beta and gamma functions. Till then, thank you, and we will continue in next lecture.